In physics, the Newtonian dynamics is understood as the dynamics of a particle or a small body according to Newton's laws of motion. Mathematical generalizations. Typically, the Newtonian dynamics occurs in a three-dimensional Euclidean space, which is flat. However, in mathematics, Newton's laws of motion can be generalized to multidimensional and curved spaces. Often the term Newtonian dynamics is narrowed to Newton's second law. Newton's second law in a multidimensional space. Let's consider particles with masses in the regular three-dimensional Euclidean space. Let be their radius vectors in some inertial coordinate system. Then the motion of these particles is governed by Newton's second law applied to each of them. The three-dimensional radius vectors can be built into a single-dimensional radius vector. Similarly, three-dimensional velocity vectors can be built into a single-dimensional velocity vector. In terms of the multidimensional vectors, the equations are written as i.e. they take the form of Newton's second law applied to a single particle with the unit mass. Definition. The equations are called the equations of a Newtonian dynamical system in a flat multidimensional Euclidean space, which is called the configuration space of this system. Its points are marked by the radius vector. The space whose points are marked by the pair of vectors is called the phase space of the dynamical system. Euclidean structure. The configuration space and the phase space of the dynamical system both are Euclidean spaces. They are equipped with a Euclidean structure. The Euclidean structure of them is defined so that the kinetic energy of the single multidimensional particle with the unit mass is equal to the sum of kinetic energies of the three-dimensional particles with the masses, constraints and internal coordinates. In some cases the motion of the particles with the masses can be constrained. Typical constraints look like scalar equations of the form. Constraints of the form are called holonomic and scleronomic. In terms of the radius vector of the Newtonian dynamical system, they are written as each such constraint reduces by 1 the number of degrees of freedom of the Newtonian dynamical system. Therefore, the constraint system has degrees of freedom. Definition. The constraint equations define a dimensional manifold within the configuration space of the Newtonian dynamical system. This manifold is called the configuration space of the constraint system. Its tangent bundle is called the phase space of the constraint system. Let be the internal coordinates of a point of. Their usage is typical for the Lagrangian mechanics. The radius vector is expressed as some definite function of. The vector function resolves the constraint equations in the sense that upon substituting into the equations are fulfilled identically in internal presentation of the velocity vector. The velocity vector of the constrained Newtonian dynamical system is expressed in terms of the partial derivatives of the vector function. The quantities are called internal components of the velocity vector. Sometimes they are denoted with the use of a separate symbol and then treated as independent variables. The quantities are used as internal coordinates of a point of the phase space of the constrained Newtonian dynamical system. Embedding and the induced Riemannian metric. Geometrically, the vector function implements an embedding of the configuration space of the constrained Newtonian dynamical system into the dimensional flat configuration space of the unconstrained Newtonian dynamical system. Due to this embedding, the Euclidean structure of the ambient space induces the Riemannian metric onto the manifold. The components of the metric tensor of this induced metric are given by the formula, whereas the scalar product associated with the Euclidean structure. Kinetic energy of a constrained Newtonian dynamical system. Since the Euclidean structure of an unconstrained system of particles is introduced through their kinetic energy, the induced Riemannian structure on the configuration space of a constrained system preserves this relation to the kinetic energy. The formula is derived by substituting into and taking into account constraint forces. For a constrained Newtonian dynamical system, the constraints described by the equations are usually implemented by some mechanical framework. This framework produces some auxiliary forces, including the force that maintains the system within its configuration manifold. Such a maintaining force is perpendicular to. It is called the normal force. The force from is subdivided into two components. The first component in is tangent to the configuration manifold. The second component is perpendicular to, in coincides with the normal force. Newton's second law in a curved space. The Newtonian dynamical system constrained to the configuration manifold by the constraint equations is described by the differential equations, where are Christoffel symbols of the metric connection produced by the Riemannian metric relation to Lagrange equations. Mechanical systems with constraints are usually described by Lagrange equations, whereas the kinetic energy, the constrained dynamical system given by the formula. The quantities in are the inner covariant components of the tangent force vector, and they are produced from the inner contravariant components of the vector by means of the standard index lowering procedure using the metric. The equations are equivalent to the equations. However, the metric and other geometric features of the configuration manifold are not explicit in